This presentation is in preparation for investigating Windows systems. This will lay some groundwork for what we need to know before we start investigating Windows systems. So here's what we're going to try to do. We're going to do a little bit of history. We're going to talk about current major operating systems. We're going to contrast application software and system software. And we're going to describe the main responsibilities of an operating system. In addition, we'll talk about memory and process management, time sharing and the virtual machine illusion, logical and physical addresses, memory management techniques, fixed and dynamic memory partitions, demand paging and the virtual memory illusion, stages and transitions of the process lifecycle, CPU scheduling algorithms. So there are two kinds of software, and you should be aware of application software. This is software that's written to address specific needs. Examples of this are going to be Microsoft Word, Internet Explorer, and so forth. They solve problems in the real world. This is why you bought your machine. On the other hand, system software manages a computer system at a fundamental level, so you may not even be aware that it's operating. It provides the tools and an environment in which application software can be created and run. So application software, word processing programs, games, inventory control systems, automobile diagnostic programs, missile guidance programs, these are all application software. This is the stuff you want. System software includes operating systems, file system software, utilities such as a disk defragmenter, compilers, maybe a web browser, the stuff you need. So today we see a number of OSs in existence. Unix, of course, Windows, Linux, embedded operating systems such as Android and iOS, and then there are real-time operating systems. So which is the best OS? Well, that depends. None are best. From a consumer point of view, buy whatever you like. A lot of people like Macs, most people prefer Windows. For a professional point of view, cost, task, maintenance, support, legacy issues, popularity, all of this plays into the equation. So let's get a little history. Mainframes began around 1950. The earliest computers had no OS at all. They were proprietary OSs, such as VMX, early Unix versions. Unix actually was invented at AT&T Bell Labs. So here's a picture of a mainframe. Notice how big it is. It really doesn't have much memory or computing power, but it's certainly big. This is another one from around 1964. So here's some more history. Let's take a look at Unix. Mainframes were often shared by many users, so obviously a multi-user OS was needed. Unix arose to fill this need. That's why it was developed. IBM, Digital Equipment Corporation, or DEC, Honeywell, Hewlett-Packard, all of these companies came together to develop Unix. Each had their own proprietary version on Unix, but it was still the same general idea. So early personal computers came around in, say, the late 1970s, and they were microcomputers based on the first integrated CPU chips. The first one just about was MIT's Altair 8800, the Commodore 64, which I fondly refer to as the Commodore 64, the Atari ST, the TRS-80, which also has a nickname, Trash 80, the Apple II, and I don't know if you've ever taken a look at Apple IIs, but they were very primitive. Each machine had their own proprietary OS, or none at all for the Altair. So the key to this was the microprocessor, and the original one that sort of came on the scene was the Intel 8080. This arrived at about 1974. And you can see the picture there. Now, if you've looked at today's microprocessors, this doesn't look anything like today's processors. The Altair 8800 you can see here from right around 1975. So let's see, PCs and Macs. PCs and Macs sort of arrived on the scene in the 1980s. The IBM PC, and there was actually a distant cousin, the IBM PC Junior. So IBM hired Microsoft to supply DOS. And that was the command line thing that you use. And Microsoft actually bought DOS from someone else. So there's an interesting story about this. IBM didn't originally go to Microsoft. They originally went to Digital, and they were going to buy a Digital system, but Digital missed the meeting, so IBM went to Microsoft. Let that be a lesson. Make sure you write down your meetings. The Macintosh, they wrote their own OS. They borrowed the idea from Xerox, and there were actually quite a few lawsuits between Xerox and Apple over the years. So the IBM PC needed some sort of a graphical user interface, or a GUI as we normally say. So IBM hired Microsoft to write OS2 for PS2. PS2 is not a PlayStation. PS2 was one of the most early IBMs. Microsoft wrote Windows at the same time, Windows 1.0, and it did have a nice user interface, but it wasn't multitasking and had quite a few restrictions. So why did Microsoft win out? Well, DOS was a cash cow for Microsoft, and Windows had backward compatibility with DOS. In fact, Microsoft has always strives for backwards compatibility with stuff. PC hardware was cheaper than Mac hardware, and another thing I'd like to add is that the PC had an open architecture, where the Mac had really a closed architecture. So it was really hard on the Mac for people to build and create and sell add-on cards. So what is Linux? Well, it's based on free source code version of Unix. The source is compiled to Intel CPU machine code. Commercial versions are available. Red Hat might be the most famous company that distributes a commercial version of Linux. Internal software architecture dates back to the 1960s. It is a multi-user OS for a single user machine. So here you see a big bag of money. It's all about the money. Linus Torvalds led the creation of Linux so that he could run Unix-based code on cheap PC hardware. He basically single-handedly wrote the original version of Linux. Where are the computers? The machines you see. Windows, almost every desktop in the USA and the world runs Windows. The machines you don't see, there are lots of Unix-based machines behind closed doors. Now, I will editorialize right here. I mostly run Windows servers, and what I do is I go out to cloud-based companies and I run a Windows server. I'm a lot more comfortable developing for Windows, and I know the rap against Windows servers is that they're not as secure as Linux servers, but they're really not bad. So why is Linux important? There are three main reasons. Academia likes it. Okay. Computer science discipline was built with Unix systems. Replacement of legacy hardware. Linux on a PC is cheaper than Big Iron. And it has internet plumbing, which is kind of baked into it. Is all Unix based, will not be redone. So why is Linux important to academia? Well, there is a lot of code and textbooks written for a Unix point of view. Linux allows you to use this stuff on cheaper hardware. There is also a lot of application code running on old expensive Unix mainframe and workstation machines. Linux is replacing these machines because it runs on much cheaper hardware. Internet routers and other hardware were originally run on old expensive Unix machines. Now Linux is replacing these machines because it runs on cheaper hardware. Learn Linux if you plan on studying computing more. And I'll interrupt you here and say that The second semester, Digital Forensics 2 here at UCF, we pretty much focus on Linux, while this semester we focus on Windows. So we have this term, Wintell, which means Windows Intel machines. And these are going to be around for a long time. They're part of the standard infrastructure. The platform is standard and widespread. There are lots of existing programs for Wintell. It does have its own legacy similar to Unix. So what are the dominant OSs? Well, Windows for the front end is the most common. Now, if you're a Mac person, I can hear you now. Yeah, Mac this, Mac that. But right now, Windows dominates. On the back end, Linux is the dominant force. And even though I develop for Windows servers on the back end, most of the world develops for Linux on the back end. So what about now in the future? Well, we have this new set of hardware devices called tablets and smartphones coming out. And these OSs are actually becoming more and more important. So the difference between them and Windows is that Windows has a maximum front end. So let's get technical. A major OS job is to provide interfaces. What do I mean by interfaces? No, not graphical interfaces, but interfaces to the kernel. Okay, sometimes we refer to these as APIs. So you have human users, and they're running application software. The application software talks to the operating system. The operating talks to other system software, such as maybe the networking OS. See, networking has its separate subsystem, the file subsystem, and so forth. And then each of these then talk directly to the hardware. So the OS is there mainly to do what we all learned about in kindergarten, sharing nicely. Remember, we've already talked about that the kernel has to be reentrant. So what the OS does is it manages the traffic between the application software and the actual kernel. So file systems, the monitor, the keyboard, the mouse, etc., etc. The OS is in charge of making all the application programs share nicely. So it gives all the application programs a way to talk to these subsystems in a really nice way where they're not going to bump into each other. So what are examples of this? Sending keystrokes to the correct application, this system of overlapping windows, making sure that apps don't access each other's memory. Remember, we talked about process space. So each process gets its own space, so they can't like write into each other's memory. And actually, in the earlier versions of Windows 1, 2, and 3, you could do that. So process management, that means sharing the CPU. So if one application would hog the CPU, then nobody else would be able to do their job. So there has to be this idea of managing a process. You also have to share the I/O devices. For instance, if you have two application pieces of software that are talking over the network, they both have to use the network card and send and receive data. Okay, memory management and disk management. So what's this idea of process management or sharing the CPU? Well, as we talked about, there's a process, and this is a program that's in execution. Process management is keeping track of processes and the states that they are in. And CPU scheduling determines which process in memory is executed by the CPU at any given instant in time. Basically, what happens is you might have multiple cores, but each core is going to split its time between different processes. So here's a little more history. We originally had this thing called batch processing, where you'd have this one big machine, one operating system, okay, and several similar jobs were organized into batches that required the same resource. Okay, so it would load the compiler and run all the programs to be compiled. Visual representation of that. So you have multiple users, and each one had their job. It goes through this operator, and it does the batch processing for the computer. Okay, so there's a different idea called time sharing. And this is where you still have one big expensive machine. And each user had their own virtual machine. The virtual machine had system resources that were available to use, but in reality all the resources were still shared. Unix was created as a multi-user time-sharing operating system. So what about from the 1970s on until now? Multitasking is the name of the game. And I remember for the Windows consumer community, that came in Windows 95. It wasn't until Windows 95 that the Windows operating system was able to multitask. Now I take that back. Windows NT was multitasking, but I'm talking about on the consumer level. It wasn't until Windows 95, and even then, it was really kludgy and wasn't that great. And what makes this really good is there are lots of cheap PC machines, and this whole idea of time sharing evolved into multitasking. So you have one user running many programs, and I typically will have lots of programs running when I'm doing my work. So Windows was created as a single-user multitasking operating system. So here's a visual diagram illustrating the process states. Okay, so you have new, ready, waiting, running, and terminating, and you can go from state to state depending on the need. So now let's talk about the process control block. The operating system must manage a large amount of data for each active process. Usually that data is stored in RAM in a data structure called a process control block. The OS maintains one PCB for each process. Processes are like several cooks sharing one kitchen. So there's this thing called a CPU context switch. There is only one CPU and therefore only one set of CPU registers. These registers contain the values for the currently executing process. Each time a process is moved to the running state, register values for the currently running process are stored in its PCB. Register values of the new running state are loaded into the CPU from the PCB. This exchange of information is called a context switch. CPU scheduling determines which process in the ready state should be moved to the running state. Many processes may be in the ready state. Only one process can be in the running state, actually running at any one time. Now, just to clarify, that's on a per core. Obviously, each core can have its own running process, but this is on a per core basis. Remember that even if you have 8 cores in your machine, each core is still going to be sharing itself with many processes. So which one gets to be moved from ready to running? Well, there's an idea of non-preemptive scheduling. The currently executing process gives up the CPU voluntarily. This is a bad idea. Windows 3.1 and before did this, and many applications could just totally hog up the CPU and make the machine virtually useless for all the other applications. Preemptive scheduling, however, is the much better option. This is where the operating system decides to favor another process, preempting the currently executing process. This was Windows 95 and later, although, like I said, Windows 95 wasn't perfect. So, what are some of the CPU scheduling algorithms? Well, first come, first served. Processes are moved to the CPU in the order in which they arrive in the running state. And this is actually a fairly trivial approach to it, and probably not that great. The shortest job next, process with shortest estimated running time in the ready state is moved into the running state first. So that meaning that the CPU is going to tackle one job and can get finished really quickly. Or a round robin. Each process runs for a specific time slice and moves from the running state to the ready state to await its next turn if not finished. Okay, so these all sound pretty simple and straightforward. However, in Windows now, it's a combination of all three, and it actually really is a very smart algorithm. So first come, first served might look like this. Shortest job next might look like this. And a round robin, well, it's just going to be taking turns. So here's an example of a round robin scheme. So now we'll delve into memory management. Memory management is the process of keeping track of what programs are in memory and where in the memory they reside. So take a look at this figure. And each one of these rectangles represents a single byte of information. It starts at 0, then goes to 1, and it'll go way up. And each one of these numbers is an address. So there are two parts to memory management. One is the address of the memory where it's located. And if you're a C programmer, this is the same as a pointer. And then the other is the contents of the memory, what the memory contains. So what's the problem with this? Well, every program wants to be loaded to RAM address 0, and that's going to be impossible. So the problem here is that everyone wants to think that they're at RAM address 0, but they can't be, because there's only one real physical address 0. So what we do is we load them elsewhere and lie to them. Okay, this is called address relocation. This is part of memory management. When we load them in, they act as if they're at location 0. However, they're not really. Track where a program resides in memory. Convert logical addresses into physical addresses. Now, a logical address is an address that the program uses. All programs start at logical address 0. That doesn't mean that's really where they are, but that's their logical address. A physical address is an actual address in the main memory device. A program may not actually be loaded starting at physical address 0. In fact, I can bet you $100 they won't be. So, single contiguous memory management. This is the simplest way. Only two programs in memory. The operating system would be first, and then the application program would come next. This would be a really easy, simple system. In fact, this is how it used to be. Way back in the DOS days, this is how it would have worked. A logical address is simply an integer value relative to the starting point of the program. To produce a physical address, we add a logical address to the starting address of the program in physical main memory. So here you have A, and then you have A plus L for the application. The logical address L translates to physical address A plus L. Okay. Partitions. This is main memory that is divided into a particular number of partitions. Programs are loaded into available partitions. This is not the same as a hard drive partition, which we'll be talking about later in this course. So here you have the operating system. You have process 1. There might be an empty block, just depending on how it kind of allocated. Process 2, process 3, and more empty space. So the operating system manages where these are in physical memory. Potentially, this empty space was filled with another process at one point, but when those processes were closed or exited, then this just left empty memory. So memory is divided into a set of partitions, some empty and some allocated. A register that holds the beginning address of the current partition is the base register. A register that holds the length of the current partition is the bounds register. So now we have another idea called paged memory management. Paged memory provides processes that are divided into fixed size pages and stored in memory frames. So a frame is a piece of main memory that holds a process page. A page is a piece of a process that is stored into a memory frame. And a page map table is a table used by the operating system to keep track of page-frame relationships. That way you don't have to have this monolithic block for a single process. You could have some pieces here, some pieces here, some pieces here, and the page map table is pointing to wherever those pieces happen to be. So this is a diagram showing you how the portions of an application can actually be split up into memory. So what is demand paging? This is an important extension of paged memory management. Not all parts of a program actually have to be in memory at the same time. In demand paging, the pages are brought into memory on demand. So then there's a mechanism called page swap. This is the act of bringing into a page from a secondary memory, which often causes another page to be written back to second memory. So you might be going, here's your memory, here's your second memory. So second memory might swap with whatever's in the memory at the current time. The demand paging approach gives rise to the idea of virtual memory, the illusion that there are no restrictions on the size of a program. Too much page swapping, however, is called thrashing, and many of you have probably experienced this at times. This can really seriously degrade system performance.